guide you back to the same concepts. Okay. So that's for introduction before we go into the lecture. Any questions for the stuff that I had just gone through? Okay, I think the good thing is I create the slides in okay, one of the classmates asked if it's not recorded, right? How will he catch up if it's not recorded lah? So I think the good thing is I create the slides in really a bite-sized manner. It's really point by point kind of thing. So I think if you really miss, let's say MC or what, right, you should be able to read on your own lah. Then if you encounter any issues, right, you just email me anytime. So if I'm free, I'll reply you all. Even midnight, if I'm free, I'll reply you all. Yeah, if I see the email, I'll reply you all. Yeah, so it's really anytime you all can ask me one. Okay, because I was told not to record the lecture. Yeah, hope you all understand. Okay, right? Okay, yeah, thanks. Okay, then if no other questions, then we can start today's lecture. So maybe halfway, today we will be going through 1, 2, 3, right? Maybe after the second one, we'll go for a short break. Then during then, I'll show the QR code for those attending online to mark their attendance. Okay, so let's begin the lecture. Yeah, correct. It's in the system, right? Can my lecture slides be found in the system? I uploaded. Sorry, you only find which one? Oh, you cannot see the slides at all. Not even at the top. Oh, let me check. When you click the course, yours is the Engineering Dynamics bracket 2261, right? It has been uploaded. Sorry, can I see your screen? Yeah. Can you all see now? If you all refresh. Can see? Under modules. No, have already. Have already. Okay, okay, good, good. Okay, I have already. Okay, sorry for the delay. Okay, let's start today's lecture. So the first topic, right, is actually quite a warm-up lecture. Okay, measurements and vectors. So yeah. So under modeling. Okay. Okay, so measurement and vectors is quite a warm-up lecture for you all. So some recap of what you all had learned before. Whatever that's learned in this topic one, right, is actually quite core knowledge that we'll be using throughout the course. Okay, so experiments require measurements of physical quantities. What are quantities, right? Every measurement gives a number, and the value depends on unit that goes with it. So after every number, right, you will see units. Let's say kg, is it meters or is it seconds? So those are units. So we have metric, we have SI units versus imperial units. We'll be using SI more often now, okay, than imperial. The British kind of units, right, if you bake, you will see things like ounces, that kind of thing, okay? As engineers, good to know, but these days, we have Google, right? Very easily, we can convert, okay? But we will use SI most of the time. It is important to agree on certain important basic physical quantities so that people can communicate with each other, okay? Like we know what quantities and units we are referring to. Okay, so there are a total of 7 base quantities. So base quantities are like length, mass, time, and then we have meters, kg, and seconds, all these, right? So the first 3 that you see here, they will be primarily used throughout this course. So we'll be touching a lot on length, mass, and time. The 4 that you see at the back, right? Current is for electricity, temperature, as we already know. So these are the SI units. And more of substance, if you do chemistry, you will see moles, and luminous intensity is for light, for measuring light. So the 4 at the back, not so important for this course. Okay. Later on, when you learn thermodynamics and things like that, you will touch on a lot of temperature stuff and mole. So for this course, the first 3 will be touching a lot on it. Physics engineering deals with many orders of magnitudes. So we use prefixes to simplify our work. So what are prefix? When we say prefix, right, these are the stuff in front of the unit that we see. These are called prefix. So when we say kilometers, right, this kilo is actually a prefix. When we say things like megahertz or megawatts, so this is prefix. When we say megawatts, right, we need to know this mega, it stands for 10 to the power of 6. Okay, we need to know. If not, we'll be seeing too many numbers. That's why we use this kind of prefix to help us. Sometimes it gets quite big for giga and tera. These days, terabyte should be quite a common term already, right? Terabyte. So that's to the big scale. So to the micro kind of scale, right? To the small scale, you also have. So milli stands for 10 to the power minus 3. micro is 10 to the power minus 6. Those I put in red we'll see more often. So for centi, right, it's actually 10 to the power of minus 2. That's why we will hear of centimeter. So cm, right, actually the centi is actually a prefix. Okay, it means 10 to the power of minus 2. That's why 1 meter is 100 cm. So that's prefix. We also may use scientific notation to replace the use of prefix. So this is just another way to describe big numbers, okay, or numbers with a lot of decimal or zero. So if you use scientific notation, right, it will look like that. 852, this is nanometers. If you write scientific notation, you write a number here, then you put times 10 to the power of something. So if you see in this form, right, this is a scientific notation. Okay, so sometimes we use this to write our numbers as well. So this is just another example. One thing good about scientific notation, right, is it allows us to know the number of significant figures. Significant figures, it tells us to what kind of precision is important. Okay, so for example, when we say 400 meters, what is the precision that we are talking about? If we are referring to the running track, right, 400 meters is correct, right? It's quite precise because that's what we are talking about. But if we describe distance to the MRT station, right, if we tell our friend it's 400 meters, so that could not be very precise because it can be 5 meters off or 49 meters off, but you still can round it to 400 meters, right? So in that sense, we cannot really tell the precision. But if you write it in scientific notation, which is below here, you can see these all, right, they represent the same number. They all represent 400. But you see the value in front. If you put a lot of decimal places at the back, right, it tells people that it is precise to that amount, to that value. So if you write 4.000 times 10 to the power of 2, right, this value cannot be 4.001 really. It's wrong because you already tell them it's precise to 3 zeros at the back. Okay, so scientific notation, it tells us the significant figures also. Okay, uncertainty. So uncertainty measurement depends on a few things. One is the quality of apparatus. So when you make any measurements, right, or experiments, the quality of the device that you use will matter a lot. If it costs $10, it's going to be off. If it's $10,000, right, maybe it can be super accurate, right? So quality, the skill of the user, it also matters. So some people can use the device better than another person. The last one is the number of measurements taken. So usually, the more measurements taken, then you take the average, right? That will give you a lower uncertainty. So we come to accuracy versus precision. So accuracy and precision, right? In terms of English, sometimes we just roughly take it as the same, but actually it means very different thing. Okay, so in physics, accuracy, it means how close it is to the correct value, how close it is to the true value. That's how accurate it is. When we say precision, right, is how many decimal or significant numbers we are talking about. Okay, that's precision. So something can be very precise up to the 10 decimal place, but not accurate because it's wrong. Okay, something can be very accurate but not precise. So they are two totally very different things. Okay, systematic and random errors. So these are two different kind of errors. Systematic errors, they are repeatable with small deviations from reading to reading. So averaging with the same instruments do not help. That means the device that you use, right? Let's say weighing scale. This weighing scale is always off by 0.1 kg. You always use, right? You think you take more values, it can be more accurate, but it won't be because it's always off by 0.1 kg. So that is the systematic error, systematic count error. Random errors. Okay, even if you know people shoot rifle, right? The rifle, they look at the crosshair, but they think they are hitting here, but they are always hitting somewhere around here. So that's a systematic error also. Okay, that's why people have to zero it. Weighing machine, you zero these days very easy, right? You just press the zero button, then it correct to zero. But in the past, not so easy. People have to manually zero it. Okay, another kind of error is called a random error. So these are deviations due to conditions that do not remain the same. So maybe due to human errors, you always measure sometimes a bit more, sometimes a bit less. So these are the kind of errors, right? Random errors. These are the kind of errors that will help when you average out the values. So far, okay? Okay, then just a recap of significant figures. So for multiplication and division, that means when we do multiplication and division, the number of significant figures in your answer, right, must be equal to the smallest number of significant figures in the input. So for example, if we have a measurement, a meter rule length measurements, one is this one, so 11.3, right? The other one is 6.3. If you want to take the area, you multiply the two together, correct? So what is the SF for these significant figures? We will follow the smallest number of SF in the input. So you go and see the input, right? This is the smallest number of SF. This one got 3 significant figures, correct? This one got 2. So the final answer, it will be 2 and not any other thing else. Okay, so that's for when you multiply and you divide. Then for addition and subtraction, we will follow the decimal place instead. So the number of decimal places equals to smallest number of decimal places in the input. So for example, if you take these two and you add together, we will follow the decimal place of this one. Smaller number of DP in the input, right? This one got no decimal place. That's why you follow this. We should have 0 decimal place in the outcome, in the output. Okay, so technically when you write out your solutions, right, should try to follow these conventions also. But usually having 3 or 4 significant figures is usually a safe choice in most answers or lab work. We don't have lab work here. Okay, so usually we will leave answers to about 3 to 4 significant figures. If you do your steps, right, let's say you will take 5 steps to achieve your final answer, right, it will be a good habit if the intermediate steps, right, you leave to more decimal place. Okay, just leave to more, you can leave to 5 or 6 so that your final answer, right, can be more accurate. Okay, no, any questions? If not, then I think in this first topic, right, this will be the only new thing that most of you would probably have not come across. Okay, so dimensional analysis, it is a very powerful tool in mathematics or physics for us to check whether our equations make sense or not. So these dimensions that we are talking about, it denotes the physical nature of a quantity. For example, your length or your mass or your time, okay, in mechanics. So in our kind of study, right, we will reduce to a combination of these 3 kind of dimensions. For example, velocity. I know we all haven't learned this yet, right? This is just for illustration. For velocity, velocity is like speed. Okay, the dimension will be your length divided by time. Okay, we are not talking about units yet. It's not whether meter or cm yet. We are just talking about the dimension itself. So the dimension is length over time. So this is the dimension. For acceleration, it will be length over time square. So below, right, the denominator, right, will have 2 of the time. Okay. Same thing for force and energy. I will not go into this because we haven't really learned yet. Later confuse you all further. So this is often used to check formula. Dimensions, right? Why we use it to check equation? Because both sides of an equation, right, they must have the same dimensions. So let's say a simple formula like this, right? F equals to ma. Anyway, we'll go through this, so no need to worry. This is just for example. If you write F equals to ma, on the left-hand side, right, F, the dimensions must be the same as the right-hand side. So it's a powerful tool, useful tool, because when you do your solutions, right, write out solutions, right, when at any point of time you realize your left-hand side and the right-hand side, the dimensions don't match, right, you should raise an alarm to yourself already. Okay, so it's just a tool to help us. So just an example of dimensional analysis. The velocity v, they tell you that it's in meters per second, of an object is given by the equation v equals to x plus yt square. And then they tell you this t, right, represents time in seconds. So they ask you what are the SI units of x and y respectively. Okay, so if you follow dimensional analysis, right, means the left-hand side and the right-hand side must have same dimensions. So V must have same dimension as X. V also must have same dimension as YT squared. So if you go and follow that concept, right, you will realize X, because it's on its own, it should have the same units as V. Okay? Then you go and compare your V and your YT square. So you ask yourself, what must this Y be? What must the value, what must the dimension of Y be, or the units, such that this whole thing, right, will be the same as meters per second. Down here got a T square, right? That means you already have a second square over here. So Y has to be of certain units such that this whole thing will be equals to meters per second. So the answer will be meters per second cube. So this is the dimension for Y. Okay, this part okay, right? So you see meters per second cube, if you go and multiply by second square, you are going to get meters per second. Okay, so this is a simple illustration of dimensional analysis. The left-hand side must match the right-hand side. So we go to a bit complicated usage of it. This is another example. Deduce the relationship between period of pendulum T and its mass m, length of string L, and acceleration due to gravity G. So down here, they tell you for these quantities, right, what are the dimensions? So for time is T, length is L, mass is m, and then this G, right, they tell you the dimension is LT to the power minus 2. LT to the power minus 2 is L over T square, it's the same thing. So this is the same as L over T square, like this, okay, same. So that's the dimensions. So the question continue, right? They tell you, suppose T equals to K, then this whole expression over here, they tell you K is dimensionless. Dimensionless means K has no dimensions. It has no units at the back, okay? K is a dimensionless constant. So they ask you to solve for X, Y, and Z. Okay, this expression means K times M to the power X times L to the power Y times G to the power Z. Okay, so how to solve for X, Y, and Z? We will use dimensional analysis to solve for these values. So if you look at this equation, from here, right, you put in the dimensions. So down here is M, you put M, L, you put L. G, the dimension is LT to the power minus 2, right? You put it in. Then the X, Y, Z, it will remain there as indices. Indices, that means the to the power of something. That's the indices. Okay, from here, you will start to compare the left-hand side and the right-hand side. So if you look at M here, left-hand side is 0. You all know why left-hand side M is 0? Anyone knows? Because M to the power of 0 is 1, correct? M to the power of 0 is 1. So you have to rewrite, not really rewrite, like you have to know that this thing down here, right, this side also have M to the power of 0. You also have L to the power of 0. Okay, M to the power of 0, L to the power of 0, then times T, because those represent 1. Now you want to compare, right, you must imagine that they are there. So you go and compare the indices. M is to the power of 0, that's why you put 0 here. Then on the right hand side, you have M here, right? So you are just comparing the indices. That's why it's equals to X. So if you compare M alone, right, you already solve for X. X must be 0. Then you continue, compare either L or T. So in this case, the solution, they compare T first. So T down here to the power 1 on the left hand side. On the right hand side, T is to the power of minus 2Z. Correct? So you put minus 2Z here. Then got nothing else already. So actually from here, right, the second step, you already solve for your Z. Okay, then last one, you are left with L. So on the left hand side, you have 0. Down here, 0. Then on the right hand side, you see L, right, got what indices? So L you have to the power Y. So you put Y here. And this term also has L inside, which is to the power of Z. Okay, so if you multiply like this, right, the indices will be Y plus Z. Okay, so from here you will solve for Y. Because the previous step you solve for Z, that's why you sum into this equation, you will get your Y. So in this manner, you would have solved for your X, Y, Z already. Okay, by using dimensional analysis, just to make sure the left-hand side and the right-hand side, they can match. Any questions? If you all got a question, can just email me or later can come and ask me, okay? Maybe you need some time to digest. Okay, then now we move into coordinate systems. Sorry, are those online? If you ask me questions, of course, no questions here, but if you ask me questions, I may not reply immediately because I only have one screen here. Yeah. If I do at home, I have another screen so I can see the questions immediately. Okay, so let's move on. Coordinate systems. Coordinate systems are to describe the position of a point in space, right? This is like our X and Y axis. Remember our coordinate systems? So 1D will require one coordinate. Usually it's just X. 2D will require two coordinates. Usually it's X and Y. And 3D usually is X, Y, Z. So these are coordinate system. So what makes up a coordinate system? They must have these things so that they can be called coordinate systems. So it must have a reference point. It must have some reference point, which is usually the origin. And it also must have a set of axes with scales and labels, so that we can define a point on this coordinate system. Okay, for example, you need to have some reference, right? Then you have an axis. Whichever point you put on this coordinate system, right, you will be able to describe it, depend on what coordinate system it is. So the first coordinate system that we are all familiar with, it is called Cartesian coordinate. So Cartesian coordinate is like the one you already know, X, Y, Z. That one is Cartesian coordinate. So you see you have an origin, you also have a set of axes. And then if you put a point anywhere, if it's 2D, it's like that. If you put a point anywhere, you can describe it by telling people the X and the Y. Okay, so this is a coordinate system. You can describe any point in this space. For 3D, it will look like that. For 3D, it will look like that. Towards the later part of the course, when we talk about mechanics of machines, right, you all will need quite a bit of understanding of coordinate systems and how the objects, right, actually will move in the coordinate systems. Sometimes they will ask you to visualize it in 3D, okay, which is like that, X, Y, and Z. The other kind is called the plane polar coordinate. Just now it's Cartesian, right? We use X, Y, Z. For polar coordinate, right, we don't use X, Y, Z. We use the angle, which is usually called theta, and we also use the length from the origin to the point itself. Usually we label as R because it looks like the radius if we go in a circle. Okay, so if you have this distance and you know the angle from the x-axis, right, you will be able to describe any point on this coordinate. Okay, so as you can see, they also can describe any point, but it's totally different from Cartesian coordinates. So how do we relate them together? Is using all this. Okay, so this is your trigo. This is your trigo, which is on the right hand side, I put here. Remember your sine, cosine, and tangent, your torcaso, right? So this is from trigo. You can convert x and y to your r and theta by using all these. And magnitude-wise, right, we will use your Pythagoras theorem to convert r to x and y, or vice versa. So these are for converting from one coordinate to another coordinate scale. So cylindrical coordinate, this term, is actually polar coordinates, but in 3D. Just now we have theta and we have the r, right? But if we do it in a 3D form, it's just another term. Okay, we call it cylindrical coordinate. Because if you have a cylinder looks like that, right? This coordinate will nicely describe a cylinder. Okay, that's hence the name. It's just 3D of a polar coordinates. Any questions for coordinate systems? Should be okay until we need to use it, then it can get quite confusing, right? The next thing, very important, vectors. So throughout this course, we will be using vectors almost all the time. So we need to know vectors. So physical quantities can be scalars or vectors. When we say scalar, right? This one, never mind. When we say scalar, it will have just magnitude. Okay, when we say vector, it will have magnitude and direction. Scalar has no direction. Vector has magnitude and direction. Okay, so the difference between scalar and vector, just remember vector, you will have direction. Scalar don't have direction. Okay, so that's the main difference between scalar and vectors. So this is how we will draw vectors. You will draw it like an arrow. The length of the arrow, right, usually will represent the magnitude. So the longer it is, let's say you are drawing a rough diagram, the longer it is, it should show that it has a greater value. Okay, and then the direction of this arrow is where the vector is pointing. Let's say, for example, force. If you are drawing a force, right, you're pushing in this direction. So you will draw the vector in this manner. Okay, so it has a direction to it. Okay, so symbols is usually written like that, but this is printed so for printed they'll print it like this. For magnitude, there are various ways of writing it. Usually we just put two straight lines beside to tell people that actually inside is a vector, but if you put two lines at the side, right, we only want to know what value it is. Equality of vectors. So these are same magnitudes and same direction. If you have vectors like this, right, although they start from different points, you see one start from here, one start from here, this one start from here. But if they point in the same direction and has the same magnitude, they are equal. Okay, so equality of vectors. Negative vector, if we have a negative of a vector, that means we will just draw the arrow in the opposite direction. But the length of the arrow will stay the same because the magnitude should be the same, but just that the direction, right, you reverse. That's a negative vector. So vectors, they are commutative also, which means A plus B will be equals to B plus A, just like our normal addition and subtraction. So for vectors, right, how do we add them up together? If you take A plus B like this, you will take the starting point of A and the end point of B, then you join them together. That will be the resultant of A plus B. So vectors is added up in this manner. Okay, so A plus B, you will have a vector that is slightly longer than the other two, and then point in the direction showing like this. Okay, because you join from the start of A to the end of B. Okay, then if you look at B plus A, like this, you will still go from start of B to the end of A. The arrow, right, you realize is actually the same direction and same magnitude also. So this is proven in this manner. It is commutative. Then vectors, they are also associative. That means if you have A plus B plus C, right, the bracket, if you put differently, right, it should make sense also. So like normal addition. Those in the bracket means you need to do them first, right? So you need to do them first. So let's say we have A, B, and C, they are vectors like that. If we do, actually, this one is this one. Actually, this one is referring to this diagram. This one is referring to this one. Okay, so if you look at this one first, right, we do A plus B first. A plus B, you will get this, we label it D, correct? So now it becomes D plus C. So you look at D plus C, you should get this as the resultant. Okay, so if you look at the other side, we do B plus C first. B plus C, you should get a resultant. Down here, we label it E. So now we need to do A plus E, correct? If you go and do A plus E, you will get a resultant like this. So you see this dark blue line, right? They are the same. So vectors are associative. It's proven in this manner. Okay, then subtracting vectors. We have been adding, right, so far. If you subtract, right, if you take A minus B, it's actually adding the negative direction of the other vector. Okay, so it's like A plus the negative of B. So let's say A is pointing to the right, B is pointing to the top right. If you do A minus B, right, you will just go A, and then the B, you go and flip it into the other direction. You add this together, this will be your resultant. Okay, so A plus B will be pointing somewhere here. Okay, then multiplying a vector by a scalar, it means you have a vector, right? Then you just multiply it by a number, which is not a vector. Let's say you have a vector here, you multiply by 5. So it will just become longer. So it means that the magnitude has increased by 5 times, but the direction is still the same. Okay, so this is multiplying a vector by a scalar. So now we have this question, is rotation a vector? Remember we say vector, it has a magnitude and direction, correct? This is the definition for vector. So we consider rotation through a finite angle in 3D about certain axis. It will also have magnitude and direction, but is it a vector? Is rotation a vector? Of course, the answer is in the next slide, but if you all take 30 seconds to think about it, maybe better. Okay, so to define it as a vector, right, we need to obey all the rules that we have just talked about, right? But if you look at this particular one, if you you consider this, you rotate 90 degrees about x-axis first. So initially it's like this. You rotate about x-axis means you flip it like this, okay? You treat x-axis as the one that's trying to hook it. Then you rotate about x-axis. So the book will tilt like this, right? Then the next, you rotate 90 degrees about y-axis. So in this state, you rotate about this y-axis. So you flip it. So it will look like that, right? But if you reverse the order, that means you do this one first, then you do this one. So you rotate 90 degrees about y-axis, it should look like that. But if you rotate 90 degrees about x-axis from this point, right, it will look like that. So if you follow this, right, you compare these two, they are not commutative, and vectors should obey this rule. That's why rotations, we don't consider it a vector. Okay, we don't consider rotations a vector. Okay. Now we come to components of a vector. This one very important. We will keep using over and over again throughout the course. Components are projections of a vector along coordinate axis. Any vector can be described by its components. So what do I mean by that? If you have a vector A that is pointing in this direction, you can resolve it into its components. That means this A, right, we can resolve it into this in the y-axis and also resolve it into this in the x-axis. In other words, right, if you do a ax plus ay, it should equal the original vector. So we are just rewriting the original vector into two other vectors that are in perpendicular directions. Okay, this is resolving the vector into its components. Okay, so this will be commonly used because we next time, right, when we have multiple vectors, they are all pointing in weird directions, right? We will want to resolve the vectors such that they all point nicely in the same direction. When vectors they point in the same direction, right, then you can do something to them. You can add them up or subtract. Okay, but if they point in random directions, mathematically we cannot add them up together. Okay, and how we resolve them, same thing. We'll be using trigo and also your Pythagoras theorem. That's how we resolve them. And unit vectors. Have you all learned unit vectors before? Heard of the term before, right? But forget lah, forget. But it's okay lah. So unit vectors, they are just a dimensionless vector having a magnitude of exactly 1. So unit vectors, they have the properties of vectors, right? Whatever we say just now, they all have it. They have a magnitude, they have a direction. But now the magnitude, right, we just make it into 1. Why we do that? We do that so that these unit vectors, right, is solely to tell us the direction only. We know the magnitude is just 1. Okay, anything you put beside 1 is just that thing, right? Okay, so this is solely to tell us the direction only. So unit vectors, right? We will introduce this kind of vectors. Following conventions are we will name them I, J, and K, and this will represent the directions X, Y, and Z. So I, right, will represent X, J will represent Y, K will represent Z. So if you see a number, right, then behind got the I behind this one. It will tell you this particular vector is pointing in the X direction. Okay, so we use these unit vectors solely to tell us which direction is pointing towards. So for 2D system, that means planar system, that means flat. We only have X and Y. This vector, the same vector we have seen just now, it can be written as A equals to AX plus AY. Just now we split them out, remember? One is AX, one is AY. Now if we write this AX and AY, right, as unit vectors, it will be like this. Okay, so there will be a vector at the end. This I represents the X component. Okay, so this AX now, it becomes just a number. This AX here becomes just a number, scalar. So it can be like 5 or 3 or 2. Okay, it becomes just a number. So this I beside it, right, will tell us this whole thing represents the X direction. Okay, then same thing, this one will be a number, and then this J tells us this term at the end, right, this represents the part that's pointing in the Y direction. Okay, so these are equivalent. Position vectors, this is just a definition. When you see the term position vector, right, it means that the vector starts from the origin. So, you know, in coordinate, right, there will be a point that we label O, right? That's the origin. If we say position vector, that means the vector, whatever you see, something I plus something J, or maybe plus something K also, that one, right, the starting point is at the origin. Okay, so position vector is just a definition for that. Because if they never say position vector, right, they just say this vector is 5i plus 3j, it can mean that it just starts from nowhere. Okay, may not start from origin, but if you hear the word position vectors, means it starts from the origin. Okay, then we come to vector addition. So how do we add the vectors up? Of course, graphically, just now we already see, right? If you have A here, if you have B here, you add them up. Of course, you take the start of A to the end of B. That's graphically. But numerically, how do we add them up? This is why we need to resolve the vectors into their components. Okay, so you have A and B, right? They're pointing in random directions. You want to add them up mathematically, you need to resolve these two vectors into components that point in the same direction. So if you take a look at A, we resolve it into AX and AY. For B, right, we also resolve it into BX and BY. Now you see they each have a component that is pointing in the same direction, correct? And because they point in the same direction, you can add them up mathematically. So if you look at the X direction, A plus B, right, the X direction, you'll have AX plus BX. So you write AX plus BX, and then you put an I behind, right, to signify these points in the X direction. Same thing for the Y direction. You add AY and BY together, then you put a J at the back. Okay, so this tells us that this term here is for the y direction. This is what unit vectors are for. And then also from this example, right, we see why we need to resolve vectors. Okay, so if you don't resolve, right, there's no way you can add these two up mathematically. Yeah, cannot, because they need to be in the same direction. Then the previous example is for 2D. For 3D, right, exactly the same. You just have one more axis, right? And then if you have vectors that are pointing in random direction, and now you have 3D, so you have I, J, K. So if you add them up together, it's the same thing. You have to resolve them into their own directions. For 3D, you have three, so you have I, you have J, you have K. Once they are in the same direction, right, you can individually add them up together, just like what we had done for the 2D. Okay, right, so far? Then, yeah, so this is actually the end of the first topic, right? So behind, usually after each topic, right, not all the lectures, so usually after the topics, I will have supplementary questions and the solutions for y'all to take a look. I won't be going through in class, but if at the end, let's say lecture 6, right, the last time I see you, let's say we have time left, right, I will pick some of these and then we go through together. But these are meant for you to take a look on your own. And if you have any questions, right, you can come and ask me. Yeah. Okay, so yeah, you have some supplementary questions. You can go and take a look. If you want to try, that's good, but if you have no time, right, because we are all working, it will be good to read and then also read the solutions and understand how the solution is derived. Okay, any questions for this topic? If not, then how about we finish 2, then we go for a break? That's better, right? Because now only 1 hour has passed. Okay, we finish 2, then we go for a short break. Wait, let me share the screen. Okay, everyone can see, right? So we will start the second topic. Okay. So just now is measurements. It's actually a recap of what you all had learned last time. Okay, what you all had learned last time is a warm-up lecture. So for engineering dynamics, right, actually the first thing we need to learn is kinematics. Have you all heard of this term kinematics? Yes, right? Because if you have taken even basic physics, let's say at the O levels or even before that, you would have heard of this term. But maybe the questions are not so complex. Okay, so kinematics, it describes motion in terms of space and time. That means in kinematics, right, we are concerned about how something moves, how a particle moves. Okay, what is the speed, what is the acceleration, how it moves, okay? And at this point, right, we are ignoring the thing that causes it to move. So the thing that causes it to move, right, we call them forces. You have forces, you push it, right, then it will have a motion. Now in kinematics, right, we are focused on the motion part only. Later, then we talk about the force. Okay, so types of motion, we have 3 main kinds. One is translational. Translational, that means you, let's say, move something from here to here. You translate, right? That's translational. Rotational is you rotate. Okay, you rotate, let's say you rotate something like that. Okay, it can be a combination also. Then vibrational, which we won't touch so so much in this course is, let's say you oscillate about a point. Okay, from here you go here and then you go back. This is vibrational. Particle approximation. So for the first part of this course, right, when we learn new concepts, we will assume that the object that we are talking about, they are particles. So imagine they are just one dot. Okay, of course, in real life, you see a water bottle, laptops, right? They are not one dot, they are a whole object. But when we talk about, when we learn new system, we assume that they are just one dot. What does that mean? Dots, right? One particle, they can only translate, but they cannot rotate. Okay, that's what it means. And this is valid when object is small relative to the whole system. This is referring to the approximation. So if you approximate a water bottle to be a particle, it will be accurate if you are talking about a whole system. Let's say you are throwing this water bottle from this point, right, to the next building. Okay, the whole system is quite huge, but the water bottle seems so small, then it will be quite accurate to assume that it's a particle. And this term rectilinear motion, it means motion along straight lines. Okay, rectilinear. Later we will come to curvilinear. Okay, so rectilinear means straight lines. There are a few ways to describe motion. These three ways. One is equation. Equation will look like that. Okay, this describes the motion. X is the position, right? Then you have an expression here with some t inside. These are just examples. These are just examples to show you that this is an equation. Okay, so if you sub any value of t inside here, you will get where the point is, right? So an equation describes the motion of a particle. That's one way. Another way is described using graphs. Okay, so if you see from this graph, right, at any point of time, you can tell where this particle is. So at 20, right, it's currently here. Later 30, it will be here. So from graph, you will tell the motion of the particle. Table is in this form. So if you have a row with the time, and then you have another row with an x, which is the position, right? You can basically tell or estimate the motion of that particle. Actually, they are all related. So if you plot this, right, you will get a graph. If you plot the table, you also get a graph. Yeah, this table, right, also is the same as the equation. Okay, they are of course related. They are describing the same particle, just different ways to describe it. So the first thing that we will learn in kinematics is the distance and the displacement. The motion of a particle is completely known if its position in space is known at all times. Quite common sense, right? I mean, it's just a textbook kind of definition. But of course, if the position in space is known, it is known, right? And position time graph, when we say position time graph, is a plot of x against t, which is the one that we saw in the previous slide. The definition of displacement versus distance so we have displacement and we have distance. This is for displacement. It is the change in the particle's position from xi, that means x initial, to x final. Okay, so it's just a change in the position. In other words, mathematically, right, you will just take the final position minus the initial one. Okay, this you will get the displacement. Then displacement, it is different from the distance travel. Okay, distance travel, it depends on the path that you actually walk. So let's say I'm here, right? Let's say I walk there, then I walk there, then I walk to the door. The displacement is actually just taking where I'm at the door, then subtract here. So very short distance, right? It's like a straight line. But distance, right, it will be a larger value because I walk there, then I walk there, then I walk there. Okay, so that's distance. Displacement can be positive or negative because it is a vector. Okay, so you can be moving there or you can be moving there. Okay, so there's directions to it. So example to show the difference between displacement and distance. This is the same graph that we see just now that describes the particle's motion, right? So the table here, if you plot this out, this is a t, so the scale is here. This is x, that means the position at this time, right? Where is it? So if you plot out, you are going to get this line. you see displacement is whatever value that you see here. Okay, so at the start it's 0, then later it's 30 because you are at 40, right? So displacement is actually this value minus this value. Sorry, this is not 0, this is 10. Okay, so 40 minus 10, you're going to get 30. Right, you compare later, let's say at time 30. Okay, at time 30, the displacement is only 6 because you are taking this value, which is assumed to be around 16. Okay, which is assumed to be around 16. This is just for example. You're not going to get something so big. Okay, this is just to show what is displacement. Okay, so it's a very short value. But if you compare distance, right, you see at these 30 seconds, the displacement is only 6, but the distance traveled is so large. Because distance travel, right, it takes into account the entire path that you walk until here. Okay, so distance is going to have a longer value. And then if you continue taking a look, right, when this thing goes negative, that means you are starting to walk in a negative direction. Actually, you walk there, right? Then you suddenly walk past the original point and go beyond. Okay, so we are going to the negative value. Displacement will turn negative. Okay, but distance will only get larger and larger because it will just add up, sum up the path that you have taken. Okay, for displacement and distance. Okay, okay, good. Then we move on to velocity and speed. So speed and velocity, actually we are talking about the same thing, just that speed is a scalar. We are just talking about a number only. Okay, speed is a scalar, but velocity is a vector. So velocity, we will tell the speed plus we will tell the direction that is pointing towards. So the definition of average velocity is defined as the ratio of displacement and the time interval. So let's say we are asked to find the average velocity, right? It's just this formula here. So average velocity is displacement. Remember, displacement is the final position minus initial position. Then divide by the total time taken. You are going to get average velocity. Okay, and dimension-wise, you can see that it's correct, right? So this is a simple case of dimensional analysis also. You see the top, right, it must be of length scale, and the bottom is a time scale. So you see it match. As we all know, speed or velocity is distance over time. Like you ride in a car or motorbike, it's kilometers per hour, right? So it's a length over time. Down here, the formula, right, whatever it is, the formula, it must be length over time. Okay, so that's dimensional analysis again. Okay, but down here, we are just concerned about the formulas. So for average, you will just do this. Then average speed, right? Instead of displacement, you will just take distance. Okay, so average speed, you take total distance divided by total time. So for example, this is the same graph again. Now zoom in at the start. Now zoom in at the start. So for average velocity at 20 seconds, we are taking the displacement over time taken. So displacement, right, we'll be taking a look at the blue line. And they estimate it to be about 28. So they assume this point is at about 38. Right, so 38 minus 10, they are going to get 28. Yeah, by 20. So you take the displacement, divide by the time taken. Whereas if we talk about average speed, we take the total distance. Of course, down here we don't know, but it will be a larger value than the displacement. You take the distance, divide by the time taken. You will get an average speed. Okay, so that's average. Average, that means over a period of time. Then you take the average. So now we have this thing called the instantaneous. Also velocity and speed. Instantaneous, that means at a particular time, right, at that instant, what is the velocity or speed? So it is the limiting value of ratio delta x over delta t as this delta t, right, approaches 0. So it's this definition, but the time scale, right, we imagine we are putting it to very small. Okay, so that we are finding almost like a particular point. So mathematically, right, that means we are doing a differentiation. Do you all remember how to do differentiation? Simple one can remember lah. Huh? Later we go through simple one. You all got hear of differentiation, right? Okay, good. So in this course, won't get too complex one. If you all need to do differentiation, right, won't have those ln to the power e to the power cosine or so many things. Won't because we are not testing math. We're testing sort of physics, okay, engineering dynamics. But of course, some you need to know, like differentiate sine become cosine. This kind of simple one you all need to know. Okay, so down here, it means differentiation. Okay, and graphically, if you differentiate, right, you are going to get the slope. So for velocity, right, you are going to get the slope of the position time graph. So again, this is the same graph. The red color one, right, is the position, remember? So if you differentiate, right, at any point of time, you are actually trying to find a slope, which is the gradient at that point. And just nice, that gradient will mean the velocity. Okay? Then instantaneous velocity is also simply referred to as velocity. So not all the time when we say speed or velocity, we say the instantaneous with it, right? We just ask you what is the velocity at t equals to 5 like this. So if we ask like this, right, we are referring to the instantaneous velocity. Okay, so it's like a shortcut way of saying that, but it's given that it's understood. If we ask you to find a velocity at a certain time, right, you are supposed to find the instantaneous velocity. Because the other one only have average, right? Average will be wrong because average is over a period of time. Okay, so for example, we have this equation. This one is x equals to blah, 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 blah. So x is the position. This is to describe the position of the particle. So now we have the equation to describe the position, right? Now we want to find the velocity. What do? We differentiate, right? We differentiate this to find the velocity. Okay, so it's dx over dt. You will go and differentiate this equation. Okay, so let's revise a bit of differentiation. If you differentiate a constant value, that means you do a dx over dt, right? This term here has no t. That's why it will drop off, it will disappear. Okay, then look at the next term. You have a t there. If you differentiate this, t will drop off. You will be left with 5 down here. Next term is a negative 0.22 t squared. How do you differentiate this? The power you bring down, then this power reduced by 1. Remember? Rings a bell, right? So if you bring down, you're going to get minus 0.44, and then the 2, right, you reduce by 1. That's why it becomes t. Okay, then the last term, same thing. This 3 you bring down, multiply, that's why it becomes 0.006. Then down here, 3 will become 2. So in this manner, right, if you do it correctly, you are going to get another equation. Equation describes the velocity of the particle. Okay, so you initially have something that describes the position, you know position, right? You go and differentiate it. Now you know all the velocity at any point of time. Okay, so if you have this equation, you can plot out the graph already. If you plot out this graph, right, it will look like this. Okay, so this is the velocity time graph. Okay, this is the velocity time graph. This one is a cubic, that's why it will look like this. There's a point of inflection. This one is a square, and then it happens to be positive, so you will expect some smiley face, right? Yeah, and just nice, it look like this. Okay, so if you graphically, you also can see some interesting points. Let's say for this point down here, you are walking to one direction, right? Then at this point, you turn behind and then start to walk backwards. So at this point, the point where you turn and try to move in the opposite direction, right? The velocity at that point is 0. You can see, right? You suddenly decrease speed until you reach 0. Then you start to move backwards. Okay, so this will match one. Okay, so these two graphs will match. This is like plotting out all the slopes of this graph. Okay? Okay so far? Okay, good. So that is a position, your distance, displacement, right? And then from there we move to velocity. Now there's this thing called acceleration also. So if you understand how to change position to velocity, right? You will know how to change to acceleration one. It's actually the same thing, just that you do it one more time. Okay. So a particle is said to be accelerating if the velocity changes with time. When you accelerate, right, that means velocity change. So average acceleration is defined as the change in velocity divided by time taken. So just now the formula, right? Remember our average velocity. We take the displacement over time. Now for average acceleration, we'll take the change in velocity over change in time. So just the top part change only. Okay, just the top part change. This is for average. And then for instantaneous, also same definition. When we want to find out the limit of this, right? When this delta t becomes very small, we want to find exactly at one point, we will differentiate this. Okay, so same thing, when you differentiate, it is actually finding out the slope at all the velocity points. So if you notice, right, the acceleration is just differentiating the position, right, 2 times. Okay, just differentiating position 2 times. So this is how you relate your position, your velocity, and your acceleration. Just now we did the first 2 run, right? We differentiate and then we get this one, velocity. So now from here, let's say you want to find the acceleration. We will just differentiate it one more time. Okay, same thing. So if you differentiate, right, you will get this expression over here. Okay, so this equation that you have describes the acceleration of the particle at any time already. Basically, you just change this t, right? You'll know what is the acceleration at that particular point. Okay, and also, if you can plot out, you'll look something like that. It's a linear graph because you only have t, right? And it's positive value, so you're going to get a straight line. Okay, so this is how they are all related. Okay, now that we know how they're related, let's look at one example. A car's velocity as a function of time is given by this expression, v equals to something, then there's t also. Okay, then in this question, right, they already tell you the alpha is 3 and the beta is 0.1. So this is already known value. So these are not unknown. Yeah, basically it's like that. This is equals to 3 plus 0.100 t squared. So it's already known now. So you have v equals to something, something, there's a t there also. Then they ask you, calculate the average acceleration for this interval. So from 0 to 5, ask you to calculate average. So you see, when they ask you to calculate average, right, it will be a time interval. When you have to calculate instantaneous, it will be at a particular point of time. Okay, that's why just now I say, let's say we never put the instantaneous word here, right? We say calculate the acceleration at t equals to 0. You must know that it's referring to the instantaneous also, because that's at one particular point of time. Okay, so for part A, calculate average acceleration. So to find average acceleration, what we need for the numerator, we need to take the final velocity minus the initial velocity, right? So those two, that's what we need to find. Okay, we are already given the velocity equation here. So we just have to substitute the values at different timings to find the initial and the final velocity. Okay, so the first one here, you sub 0 into this one, you are going to get velocity that is initial because they tell you initially is at t equals to 0, correct? So you are going to get the initial velocity. Then you sub 5 into this, you are going to get the final velocity. Now you have the initial, you have the final. Just put into the formula, which is difference in velocity divided by time taken. So this value here is the average acceleration. Okay, any questions? Should be okay lah, huh? Then part B, calculate the instantaneous acceleration. at 0 and 5. So to calculate instantaneous, right, we first need to go and differentiate. Because for instantaneous, we need to know it at a particular time, right? They give the velocity equation. You know, you differentiate the velocity equation, you can get another equation which describes the acceleration. So that's why the first step is to go and differentiate. dv over dt is differentiation of the velocity equation, which is already given in the question. Okay, so you differentiate, you're going to get 0.2t. Okay, then down here, you just have to sub whatever they ask you to find. So part 1, they ask you to find 0, so you sub 0 inside, you'll get 0. So it tells you that at the start, right, when it's at 0 second, it has no acceleration. Part 2, you sub 5 inside here, it will tell you at 5 seconds, the particle, or rather the object, has an acceleration of 1 meters per second square. Okay? Okay, good. So if okay, then we move on. Now we are going to some equations to describe the motion. Okay, to describe the motion. So usually when we do this kind of thing, right, back in physics, we will have derivations, correct? We try to find which one equals to what. We move things here and there, then we try to derive the equations. So for this module, right, we will not test on the derivations. So usually the slide, I will just briefly show how it's derived. That one won't be tested. Okay, so as engineers, it's more important that we know how to use the equation that's derived. Okay, because we're not scientists, right? More importantly, we need to know how to apply and use it. Okay, so just very roughly, how we get the equations. There are a total of 4 equations, okay? So this is the first one. A equals to dv over dt. This is when we acceleration, you differentiate velocity, right? Then if you put them to one side, you move the dt over, it will look in this form, look like this form. So how to solve for this? When you have d here and you have d here, we will integrate. We will perform an integration. Okay, when you integrate, right, you're going to have a constant coming out, then you will try to solve for it. But I won't go through how to solve for it. So in the end, you are going to get an equation that looks like that. Okay, this is our first equation. This means velocity equals to v naught. When we put something naught here, right, that means the initial value. This is the velocity. You can take it to be the final. Then this is the initial velocity plus acceleration times time. Okay, so that's the first equation. To come out with the second equation, right, we look at this instead. Just now we look at A, right? Now we look at V equals to dx over dt. And then about the same method, right? You move them to one side, the dt, and then you need to perform some integration. So if you go and solve that, you are going to end up with this equation here. Okay, which we'll be using also. This is x, which is the final position, equals to x naught. This is initial position, plus v naught t. V naught, remember, is the initial velocity. Okay, then plus half at squared. A is the acceleration, t is the time. Then to get the last two equations, we use the first two equations, then we eliminate t from these two equations. Okay, basically we'll do some algebra and then we eliminate t. So we are going to get the third equation, which is v squared equals to v naught squared plus 2a, then this is the x minus x naught. This you can also see it as displacement. Okay, because x minus x naught, the final minus initial is the displacement, right? So it's a displacement here. And then if we eliminate a, we're going to get our fourth equation. Okay, so this is our displacement equals to half v plus v naught t. So in summary, these four equations, right, they are very important and we will be using it for kinematics, not just 1D. We are learning 1D now, that means just movement along a one line, right? But for 2D and 3D, you will realize these equations will apply also. Okay, and these are only valid for constant acceleration. Constant acceleration means the acceleration throughout this journey that you are looking at, right, cannot change. It can have acceleration, but the acceleration cannot suddenly, like t equals to 2 is 2 meters per second square, right? Later change to 3 or 4 like this. Then the equation is not valid already. It's only valid for constant acceleration. Okay, so we have other ways of writing out the same equations also. So if you refer to different Google sources, right, or different textbooks, you are going to get different ways of writing out the same equations. There's no correct way. So I'm going to write out another way that may be easier for some of you also. There's no correct way. It's entirely up to you. So the first one, right, usually we'll write it as V equals to U plus AT. So U, right, we will usually use it to denote initial velocity. It's easier to say also, V equals to U plus AT. If not, you have to say V naught, which is harder to say and memorize. Okay, the second one is actually to memorize, right? It's easier to use S equals to UT plus half AT squared. S, right, stands for displacement, okay, which is easier to memorize also. So if you see this equation down here, if you move the x naught over, right, it's x minus x naught, correct? That's actually your displacement. Okay, so it's the same equation. Some textbooks or sources will use this, some will use this. Third one will be b squared equals to u squared plus 2as. Then the fourth one will be s equals to half v plus u, or u plus v, is the same thing, up to you to memorize. V plus ut or u plus vt. Okay, so these are equivalent equations. Okay, I personally would prefer this one, because don't have the not everywhere. They are harder to, more things to write also, and more things to say. Okay. Okay, okay, then we continue. So let's take a look at one example. A car 3.5 meters in length approaches an intersection that is 20 meters wide. The light turns yellow when the car speed is 20 meters per second, and the front of the car is 50 meters from the beginning of the intersection. So it's basically illustrated here. They tell you the initial speed. They also tell you the length of the car. They also tell you from the front of the car, right, to the intersection is 50 meters. And the intersection is 20 meters wide. Okay, so basically it's just an illustration of whatever is described here. If the driver steps on the brake, the car slows at minus 3.8 meters per second square. So this is an acceleration, right? Meters per second square, that's an acceleration. And negative here, that means it's trying to slow down. So it's a negative acceleration. If he instead steps on the gas pedal, the car accelerates at 2.3 meters per second square. The light stays yellow for 3 seconds. Ignore the driver's reaction time. To avoid being in the intersection at the instant the light turns red, should the driver step on the brake or the gas? So the light stays yellow for 3 seconds. The criteria is when it turns red, no part of the car should be in the intersection, right? So should he step on the brake or should he step on the gas pedal? So how do we go about doing this question? At the top here is basically just and another rewriting of the same question. Okay, so V naught, this is the initial velocity. This is the first case, the acceleration, right? When you step on brake, it's a negative acceleration. A2 is the second scenario where you have positive acceleration, and the time taken will be 3 seconds. Because the light stays yellow for 3 seconds. So we look at different scenarios. One is if he presses on the brakes, we want to find out how far would the car have moved. So we will go and find the correct kinematic equation for us to get the value. Right? Look at what value you have here, what info you have, and see what else you want to find. Okay, so in this case, we will be using this equation. This is our S equals to UT plus half AT squared. Okay, S equals to UT plus half AT squared. So U we already have, which is the initial velocity, same as V naught. T is given 3 seconds. This half AT squared, right? We also know already because they tell you the acceleration is minus 3.8, and then the time we also have. So you have all the info to find whatever you need. In this case, is the distance traveled. So if you put in your calculator, you're going to get 42.9 meters. Okay, that means after 3 seconds, you step on brake. He's just here, haven't reached 50 yet. Okay, but let's look at another scenario. If he presses on the gas, that means he accelerates. The car would have moved. Then you use the same equation because you have the same values, right? Same kind of values. So this is also S equals to UT plus half AT squared. You put in the values, but now instead of minus 3.8, you'll be using 2.3. That's the acceleration. Okay, so if you work out this equation, you are going to get 70.4. That means from this point, right, he will be at 70.4 meters later. So why down here, this solution, they put negative, put smaller than 73.5 because we are comparing to 73.5. Why? Because the intersection is 70 meters, right? But just now we used the front of the car as reference. But the car itself has a 3.5 meters or so. So we need to compare to the whole thing. In other words, if you move forward 70.4 meters, right, the backside of his car will still be inside of the intersection. Okay, right, this part. Okay, so it's slightly some logic kind of thing. Okay, so to answer this question, right, he needs to step on the brake pedal to fulfill what the question is asking for, the criteria. Okay? But if we continue, we take a step further, right, to analyze the problem. But logically, should he step on the brake? If he step on the brake at t equals to 3 seconds, right, that means when it turns red, actually the car has not stopped yet. Just now to meet the criteria of the question, he's not in the intersection, right? He's just nice a bit off, haven't entered yet. But actually the car has not stopped yet, right? It has not stopped. So we want to go and calculate the time where the car will come to a stop. Logically, so the car will only come to a stop T1, where then we use this equation to calculate. This is our V equals to U plus AT. This is from V equals to U plus AT. This one. Okay, so V down here, they put at the right hand side. Why V we put 0? Because we want to find out when it stopped, right? When it stopped, the velocity is 0. So the final velocity, we put it as 0. Okay, so that itself is actually one information. Okay, then U plus AT, the U, right, initially you are traveling at 20, so we put here. Then this plus AT, this part, the acceleration we are braking, right, that's why it becomes minus 3.8. Then you realize from this equation, right, you have only T1 to solve. Okay, so if you go and solve for your T1, it tells you it will take 5.3 seconds to reach the stop point. Okay, it will take 5.3 seconds for the velocity to become 0. Then you realize something is wrong already, because 3 seconds, he's here, but he only stopped at 5.3 seconds later. That means he confirmed will exit lah. So if you want to take another step further to find where he will actually stop, right, you will use kinematic equations again. This is from S equals to U plus AT. But now, right, instead of the T, just now we put 3 seconds. Now we put 5.3 seconds. Okay, so that we can find at 5.3 seconds later, where actually is the car in terms of position. So you're going to get this value 52.6 meters, which is wrong already. That means he's inside. Okay, but this is taking the question a step further to analyze. Okay, any questions so far? So this is how we use kinematics. This is 1D because the car is moving in a line only. The car is moving in a line only. For 2D, right, is the next topic, which we'll be doing after the break later. Okay, if no questions for this one, then we continue to free fall. I think you all know what free fall is. So all objects when drop something, it will fall towards the earth. For us, it just drop towards the ground, right? Because earth is below. And they will drop with nearly constant acceleration. But as we reach the end of engineering dynamics, right, we are going to study space mechanics. So when we study that, acceleration may not be the same. But for most part of the course, right, we will take acceleration to be constant because we are very near the earth. Okay, when we do space mechanics, suddenly we zoom out, then the earth becomes very small. We are talking about accelerations very far from earth. Or if we talk about whether it's your chair, your car, your water bottle, we are all very near to the earth. Okay, so we'll take it as constant acceleration. If air resistance can be neglected, then the motion, we say it is free fall. And this free fall acceleration, right, or rather acceleration due to gravity or gravitational acceleration, we will use this value. So it's just a constant number that we need to solve problems where objects are dropped. Okay, so if we need, we'll be using G equals to 9.8. Some people use 9.81, but you should get about the same answer. Okay, you should get about the same answer. You can use either lah. Okay, you can use either. Just use 9.8 lah, but if you use 9.81, I will mark you wrong. Whether an object is moving upward or downward, it will experience an acceleration downward of magnitude G if it's in free fall. So whether the object is moving left, right, you throw up or throw down or let it fall in its own right, there will always be this same acceleration trying to pull the object down at this value. So if you follow this, right, it is actually a 1D motion under constant acceleration, which means free fall problems, right, you can also use the 4 kinematic equations to solve as well, because it's actually just a 1D motion with constant acceleration. Remember, constant acceleration means we can use the equations, right? By convention, the vertical direction y is positive upwards. So when we try to do problems, right, we like to draw positive upwards. So if we follow this convention, then the acceleration due to gravity will be pointing downwards. Okay, that means A, in this particular case, will be minus G. Okay, so if you follow this particular case, where y is pointing upwards, you are going to get these kinematic equations. Of course, there's another one it's missing here. Okay, you are going to get these equations. Because if you look, for example, the first one, right, this is actually our V equals to U. This is V naught, which is U. Down here is supposed to be plus AT, right? But now this A becomes minus G. That's why the equation turns to become like this. But this is only valid for this specific case where you point y upwards. If you go and have solve your problem, right, where you point y downwards, that means you set your own coordinates as y downwards, correct, point downwards, then all these will not be valid already. Okay, so it's only valid when you point y upwards. So my suggestion is, this is just for reference, but when you solve the whatever problems, right, just use the 4 general equations. Okay, just use the 4 general ones. Okay, here's a concept question for you all to think about. The graph shows the velocity versus time graph for a ball. Which explanation best fits the motion of the ball as shown by the graph? This is a velocity time, velocity time. So which of these will fit this the best? Yeah, you all take a minute to think about it. Those people online can hear me? Sorry, I just saw the message. Okay, thanks. Thanks everyone. Okay, who thinks it's A? Anyone? Who thinks it's B? C? D? E? Okay, actually, I'm like you all, I wait for answer also. But it's okay, everyone got their own learning style. I also wait for answer, also can learn, it's okay. Okay, so the correct answer is B. B for boy. The ball is rising, hits the ceiling, and falls down. Okay, so why you see, so the ball is rising, right? When you throw a ball up, what will happen? It will slow down, correct? So velocity will decrease. So it fits the description, right? Then at this point, you see it's about the same magnitude down here, same magnitude. Imagine, for example, maybe this is 10, maybe this is 10, maybe this is minus 10. You see it's about the same, right? But what happens is suddenly change direction. That means it must have hit something. It must have hit something. Just the direction changed, but the magnitude remained about the same. You imagine a ball, let's say 100 meters per second, right? Hit something, what will happen next? You will fly back about 100 meters per second, right? Just that it's in the opposite direction. Of course, we are not talking about energy loss or anything here. Okay, so it suddenly changed direction. Then after that, what happens? Because now it's falling down, right? It will speed up. Speed up in the opposite direction. So from the graph, you will see you will get more negative. Bigger negative number, that means it's speeding up, but in the opposite direction. Okay, so answer is B. Okay, everyone? Okay, If not okay, can tell me, as in I can explain again, but all okay, Okay, good. Let's look at one example. You're on the roof of a building, 46 meters above ground. Your most hated friend, who is 1.8 meters tall, is walking alongside the building at constant speed of 1.2 meters per second. That means this is 46 meters tall, right? You are here. Your friend is walking towards the building, okay, at 1.2 meters per second. If you wish to draw an egg on his head, where should your friend be when you release the egg? And they tell you assume it's free fall. So generally, if you look at this question, right, if you understand it, it's trying to ask you, it's trying to see whether you know the egg is dropping, right? It will take some time to reach the bottom, correct? While your friend is still walking. So you need to time when he's a certain distance away, you need to start to release already. Correct. And then they ask you, what is this distance where you need to start releasing this egg? So to find the time taken to reach the correct height, that means from the top here, you want to reach 1.8 meters. Okay, we need to find the time taken. You will use your kinematic equations. This is using whatever is written in the notes. Okay, so just now it's x, right? Down here we're looking at y, but it's the same thing. Okay, so you have y equals to y naught plus v naught t minus half gt squared. Actually, the general one is plus at squared. But why become minus? Because it's going downwards. Okay, it's going downwards. And in this question, right, we define upward as positive. So this question, we define upwards as positive. So this is positive y. That's why chi will be negative. Okay, so from this equation, right, first thing you straight away know this term will go to 0. Because this is initial velocity times time. And the initial velocity, right, if you analyze the y component, you drop from rest, correct? When you drop things from rest, its confirmed starting velocity is 0. Then after that, it will increase and increase and increase. Okay, so this will go to 0. And then from here, you just put in your values. Y, which is your final height, right, is at 1.8. So they take reference from here. This is the reference. They take the floor as reference. So you want to reach a final height of 1.8, correct? Positive 1.8, so you put 1.8 here. Then starting, right, where are you? You are 46, right? You are 46 meters, correct? So you put your starting initial position. Then this one 0. After that, you continue minus half. This one g, you put 9.8, and then t squared. So down here, you realize t is the only unknown which you can solve. Okay, so if you solve for t, that tells you the time. In this case, it's the time taken for this thing to occur. So when you drop from the top to reach 1.8, it will take 3 seconds to reach that height. So from here, you can estimate where your friend should be already, right? Because the position or distance equals to your speed times time. So you take 3 seconds, right? That means he needs to be 3.6 meters away. Because this is speed times time, will give you the position, or rather the distance away. Can? Okay, understand? Yeah. Sorry? Okay. So one of the classmates asked, why is VOT 0? So this VO, right, we say V naught lah. So VO, if you write VO like that, right, we say V naught. When we put a naught, that means a 0 there, right, we are referring to the initial value, usually referring to the initial value of whatever it is. So if we put X naught, we are talking about the initial position. If we put V naught, we are talking about the initial velocity. So in this case, the initial velocity is 0. The initial velocity is 0 because we are looking at the y direction only, right? So we are dropping something. So the starting initial velocity is 0, correct? You just release like that. At that particular point, it is not moving yet. So it's 0. After that, because something is pulling it down, right? Gravitation. That's why it starts to increase speed. So whenever you do a release of something, you are not throwing it down, you just release only. The initial velocity is sure 0. Okay, right? So this is what it is lah. Okay, any other questions? Okay, if not, then we continue, we move on to another example. An alert hiker sees a boulder fall from the top of a distant cliff and notes that it takes 1.3 seconds for the boulder to fall from the last third of the way to the ground. What is the height of the cliff? So from here, it falls free fall. So at the start, it's 0 meters per second. Then let's say we say the cliff is h lah. It has a height of h, capital H. They tell you the last third of the way, that means the last 1/3, it takes 1.3 seconds to reach the ground. So they ask you what is the height of the cliff. You see like quite limited info, right? But actually you can solve one when you take simultaneous equation. So you let, in this case, we let capital T be the time it takes to fall to the ground. So the entire T, we let it be capital T. Okay. Okay, because the small t we have already used for the last 1/3. Okay, but if problems like that, you because you are writing out, right? Don't confuse yourself. Maybe some of your handwriting, the capital T and the small t look the same, right? Later after a while, you confuse, but you think the small t is the capital T. That can be a mistake also. Okay, so maybe you want to use another alphabet to represent also can. Just something that I noticed, something that I noticed. Okay, but in this case, it's typed out, so confirm no problem. Okay, so the time taken from the top to the bottom is capital T. So we can write out an equation for that. What equation you will use? You will use this one. This is from S equals to UT plus half AT squared. Okay, this equation is from S equals to UT plus half AT squared. So if you take a look at the equation, right? S is the displacement. That means distance traveled also same. It's the whole thing, right? From the top to the bottom. That's why it's H. So the right hand side, this UT, right? Why it disappears? Because initial velocity is 0. Okay, so this UT disappeared. No more, not there anymore. Then you're left with this half AT squared, which you will put in. Okay, so half AT squared, the time taken is capital T, and then acceleration, they put G. In this case, right, they never write a negative sign because they take downward as Y positive. Okay, so you can, it's up to you. When you solve problems, right, you define your own axis. If you take downward as Y positive, right, you have to stick to it throughout your entire solution. If you take upwards, you have to stick to it. But at the end, right, you realize you will get the same answer. You will get a value that is pointing in the same direction. Okay, so we do that, we get half GT squared. And then another equation that you can write out, right, is you cannot straight away use this 1/3 because you will have not enough info. But what you can do is you can take a look at the first 2/3 of the journey. Why you want to use the first 2/3 of the journey? Because you want more info, right? The first 2/3 of the journey, you know the initial velocity is 0. That one is information that you want to squeeze. You want to squeeze from. That's why instead of the last 1/3, you will use the first 2/3. Okay, so you know the initial velocity is 0. Purposely one. Okay, so the first 2/3 actually is the same equation. So the first 2/3 of the journey, which is 2/3 H, equals to half AT squared, same thing. But now the time taken, right, is this capital T, which is the whole thing, minus the time taken at the end. Right? If you take the whole thing, the time taken minus the last part, you should get the time taken for the first 2/3 journey. Correct? That's how we get big T minus small t. Okay, yeah, so now you see, you have one equation, you have two equations. Then down here, right, you only have two unknown, capital H and capital T. The small t is already known, it's 1.3. So from here, right, if you get these two equations, you will know that you will be able to solve the problem already. It's just whether mathematically you can continue. Correct? Two equations, two unknown. So the next few steps here is just trying to solve for the unknowns. Okay, so what they do here is, first they get rid of the H. You could have your own way of doing it, but then this solution, right, they substitute this H, this whole thing, they put inside here. Okay, they put the whole H inside here, so the whole thing, right, H disappeared, left with capital T. Then they solve for that. So they find capital T is equals to 7.08 seconds. That means the time taken from the top to the bottom, it takes 7.08 seconds. But actually the question never asked us to find that. But you will somehow find that because two equations, two unknown, right? You have to solve both. Then you can easily put this T back into either equation. Okay, of course you will put in the simpler equation. If you put T right back into this down here, you will be able to find your H, which is the height of the cliff. Okay, right? Okay. So this is the way to find height of the cliff. And you see, the height of the cliff, right, is a positive value. Okay, it's a positive value, positive 246. Why? Because you define downward as positive. We start from the top. So this question, they take reference from the top. So down here is the reference actually. The top is the reference. Then the axis actually starts from here. Okay, downwards, y positive. Something like that. Okay, so if you solve for this h, right, it will give you a positive value all the way to the bottom. But let's say at the start, right, you go and take reference here, but you go and take y positive upwards. Your answer, right, will have a negative sign at the end, which tells you your assumption is in the wrong direction. Okay, it should be in another direction than what you had assumed, which is same thing, right, going downwards. Okay, so whichever direction you take, x also, whichever direction you take, it should give you the same answer at the end. Magnitude-wise, whether positive or negative, of course, your answer and your friend's answer may be different because of different axes. But they should be pointing in the same direction, according to your axis. Okay, right? Okay, then after this is just supplementary questions for you all to own self go and read. Any questions so far for this part? If no questions, then I think can take a 20 minutes break. Okay, 20 minutes break. I think 20 minutes should be enough lah. Don't take too long lah. So if can end early or end early lah, so all can go home and rest. So we will continue at around 8:50. 8:50, we'll go through one more topic. Okay, so those present here, right, if you haven't scanned attendance, you can tap at the thing at the back. Okay, tap your card. Then those online one, now I'm going to show you a QR code, which you all will key in your name lah. Then I will mark manually later. Okay. Okay, so see you all 8:50.